Morning.
Hey, Ken.
We started recording. So this week we're talking about graphs and how they're represented, and so we'll start with that. So in general, a graph is a collection of vertices and edges. So you'll usually see sort of written like that, G equals VE. Well, you could even make that bigger. That would make a lot more sense. There we go. And so when you run into this, that's what you'll see, right? There's vertices, right? A bunch of vertexes, I guess you can know they're vertices, and edges. So I have here like a bunch of vertices, and then edges can go from one vertex to another. And that's what it is in general. There are some I don't know, variations on this general idea. Some of these edges may have weights associated with them. Right, so from vertex 5 to vertex 2 has a weight of 23 associated with it. So I don't know, it may cost 23 cents to go there, or it may have a maximum capacity of 23 cars, or it may take 23 seconds. Is that what I had already said? I don't know. So just depending on what thing we're graphing, they would have a different meaning. And then again, the weights may or may not include negative numbers. Sometimes negative numbers don't make sense. Like for instance, there's no such like distances wouldn't be a negative distance. Time wouldn't be a negative time, but money might be a negative amount. So depending on the circumstances, you would have different things. Or the edge show that there is a connection or not. So for instance, you can have unweighted edges, where it's just like you can get there from here to here. Generally, the way of handling unweighted edges is to use weighted edges and just assume that all the weights are 1. And so that there is an edge, meaning that there's a 1 there, and that's the weight for it. And then just ignore them in your calculations. There's also an undirected graph. Now here I have arrows on both sides, because that's kind of how I think of an undirected graph. But a lot of times, an undirected graph would just have like connections without the arrows. Apparently that's not the default, right? So that these two would be just connected in some ways, like equivalence classes. Like if A is equal to B and B is equal to C, then A is equal to C. That type of like thing can be represented by a graph. Again, if we have an undirected graph, we can kind of use a directed graph, right? The first one we talked about with weighted edges, and assume that there's an edge from here to here and from vertex 2 back to vertex 1. So we can assume that it's sort of a double arrow. We can give edges in both directions, and we can give them the same weight. So I guess the point of this is saying that, well, the most general case is to write all your stuff for weighted edges, and edges have a weight, and then they have a from and a to, and then the from and the to just can't be alternated. So when we talk about an edge, we're going to have a from and a to. So here's another variation, a self loop, right, where the from and the to are the same in it. And then using that idea, we can kind of, I don't know, we want to ask certain questions about it. Oh, here's another variation, right? We can have multiple edges from one place to another place. So it needs to be able to perhaps handle that. Needs to be able to perhaps handle self loops. Like you can think of that as having I don't know, 2 pipes from there to there, or I don't know, two connections to the internet, each with a separate bandwidth, or you can, so you can kind of, you can come up with reasons for having all of these pieces and doing that, depending on what you're trying to represent. There's some questions that we want to ask about graphs. One of those things that we're often interested in is to know, is there a cycle in the graph? A cycle would be, right, like here's a loop. We get from there to there to there. Some graphs have cycles, some graphs don't. By the way, if you have an undirected graph, right, because here's, right, just going back and forth to each other because the edges point that way, right? The self loop would always be a cycle. So for directed graph, so I guess the question is in a directed graph, does it have a cycle or does it not have a cycle? Another question is it connected? Can I reach every node from every other node, or can I reach some node from another node? So those are the types of things that we're going to ask about these graphs. The first concern we're going to have, though, is how we represent this in the computer. One way of doing these is with an adjacency matrix. A matrix is just a 2x2 array. And we're going to decide that one of them is going to be a from, and one of them is going to be a to. Again, it doesn't have to be this way. We could alternate from and to, right? It would just flip it. And then, so for instance, I can go from A to B, right? From A to B. So I'm putting a 1 there. If there was a weight on that, I would put the weight in here. So from A to B costs this amount, let's say. So that's the idea of an adjacency matrix. And you can see that this matches it. Like, so from here, C, nothing goes into C. All right, so from C, you can't go anywhere, right? Going out, right? So these would be sort of the outgoing edges or from C. And then the incoming edges, right, which would be going into C, right? There's nothing in there also, right? They're all zeros. So 0 is going to mean no edge. Otherwise, we're going to put the weight or 1 if we're not doing, if we're not concerned about the weights. So a self loop would be here along the diagonal, right? So if I had from F looping around to F, I would put a 1 there in order to demonstrate that. If the graph is undirected, that means that every time that something can go from B to A, we go from A to B. You don't really need to look at the whole graph. We just need to look at half of the graph, right? This side over here, because it would be symmetrical along this diagonal, right? If I went from A to B, I'd go from B to A. If I went from D to A, I'd go from A to D. So it would be symmetrical along here. And you can use this or we can manipulate this matrix to find information out about the graph, like is it connected, not connected. To do that, here's another thing. If you wish to make money, buying money, one of the things you could do is build an adjacency matrix that contain exchange rates. And then go through here and find out a cycle where you earn money. So like for instance, I can go from pounds to euros to pesos back to pounds, and I made 30 cents because I exchanged money or something like that. So here's an example of where you would use an adjacency matrix, because every one of these things would have a value in it. She didn't copy those other values because I don't know what the values are. But I know that you're not going to exchange 10 pounds. So actually, it'd probably be, right, if I give you $7, you give me $6.99 back or something like that. So that a fee would be charged. So that's an idea, or just a reason for doing that. This is very visual, right? We can kind of, especially taking our math courses, we've seen these matrices lots and lots of times, and we know how to manipulate them. There's lots of code around that manipulates matrices and can use them. So that turns out to be kind of a useful representation. There's some issues. If I have an undirected graph, right, half of it is wasted. And also if I have a sparse graph, right? If we talk about the number of edges, let's say the number of possible edges versus the number of vertices, and this would be written as E in the absolute value symbol would be the number of edges. I want to change the font here. Right. And V, E is right. So we'll see these, and then we know that E is less than or equal to V squared. I need to find a little thing that lets me. Oh, there we go. Superscript. All right, so I need to turn that off. Well, so that the number of edges, it can be a lot higher than the number of vertices, and so if there aren't a lot of edges, then yeah, we may have something that's very sparse, and there's just lots of wasted space in this table to do things. So, a couple of different ways of doing it. Yeah. Let's move on to the way the book does it. The book is going to keep a map, and the map is going to contain each vertex as the key, and then it's going to have a map, well, or maps. Oh, okay. Yeah, here's our outgoing edges only. It's going to have a map of where it goes to, where again, the vertices are the keys. So it's going to be a map from vertices to maps. And then this map will be a map of edges, which is going to be where I go through. So in essence, to access this spot here, I have some text there. Okay, if I put in, let's give these maps names. Let's call this one call it graph, and then this map would be, oh, I don't have room. All right. To get to this, and then here, an edge. This is getting more complicated than I wanted, right? But it exists. Let's see. Let me shrink this one down too, so it all fits. Well, that's getting tiny. Okay, so this would be graph of A. right? So that would give us this spot. And then graph of A gives us another map, so we can directly write C. It's equal to that edge. Now, this is not exactly what we're going to do, but this is the idea, is that this works like matrix, but it's not. It's not a two-dimensional array like it would look like in a different language. This is a map that returns a map. So this, right, you can think of it having a set of parentheses here, right? So it returns this map and then looks up C in this map. Right? So yes, it does kind of look like a matrix. And we can access the edges in this way. This is storing edge in there. I could also look it up and see if it exists or doesn't exist, and that sort of stuff too. So using this idea of we're going to use maps as opposed to, right, a matrix, but they kind of give you the same notation for using it. Now, this is the idea behind the way the book works. So let's look at the book's code. I've already made a copy of it. It's here in 21 graph. So let's look at the graph class itself. So a graph has vertices, or a vertex in it, and it has edges. And inside each of these, where's the element? Okay, so each vertex is going to have just an element, right? So something that's going to be passed in. This element is going to end up being a name. So this is going to maintain a map of outgoing edges, like I showed, and then perhaps a second map of incoming edges, right? Depending on whether we pass in a true or false into the constructor for the graph. So let's look at what that means. That means that when I create an empty graph, right, outgoing is going to be an empty map, and incoming is going to be an empty map. Let's assume it's directed. Right, so an empty graph contains two empty maps, right, because there's nothing in it, right? There's no vertices. Now let's add a vertex and see what happens. I'm going to have add a vertex with CHI. So adding a vertex. And this kind of is going to show us how all this works. Here we go. Insert vertex. So I'm going to pass in CHI, right? And this is going to create a vertex called V, create a vertex called V, whose element is going to be like CHI. So V here is a vertex, an object of the vertex class. This is what we're going to use in our map. We're not going to use CHI, which is a string, which is the element. We're going to use that actual vertex as the key in the map. And if it's directed, we're going to use it in the incoming map. Right? So we're not using CHI in here. You can't look up CHI in outgoing. You can only look up this vertex, right? So the vertex is going to be in here, and the vertex is going to be there. Both of those vertices are going to be in the outgoing map. One more time. Let me do it again. Let's insert Miami. It's going to create a vertex called Miami, and it's going to be the key in the outgoing map and a key in the incoming map. Right? So I've added two vertices, Chicago and Miami, and we have maps that use the vertices, not the string, the vertices. That's very, very important, that are used in the maps. So I can say, for this vertex, what edges are there? Well, there's no incoming edges. I'm sorry, for this vertex, there's no incoming edges. For this vertex, there's no outgoing edges because the map is empty. Now, the other piece in here, besides a vertex, is an edge. Let's look and see what edges contain. Oh, I just went past it. Edges contain an origin, a destination, right? A from and a to, although these are better words than from and to, and then a weight, right? The element that's associated with the edge itself, right? So the constructor has three arguments. It's got an origin, an edge, and a value. All right, it says use edge insert. So let's look at insert edge. And see what happens. So we're given these two vertices. Right? These aren't strings or anything. These are vertices. So we're going to throw errors, right, if they aren't vertices. So if I pass in CHI, it's going to throw an error. If I pass in the vertex that contains the element CHI that we already added to the graph, then it's okay. These are very similar to the positions that we used, right? Not the values, but where they are in the graph. So these are kind of like keeping track of positions, pointers, if you like that. All right, so we're going to see if we can make an edge. If there's already an edge, we're going to yell. If it'll make, I think here is where it checks for errors. Anyway, then we're going to create a new edge from U to V with a value of X, and then we're going to pretty much treat this as if it was a two-dimensional, like a two-dimensional array, and say outgoing of U, right? U is where it's going from. V is going to be that new edge that was created, and then it's also going to make an incoming edge, right? By alternating the points. So an incoming edge is here, it's the destination, here's the origin, right? So outgoing, here's the origin, the destination, incoming, here's the destination, and it's the origin. So you can follow these backwards if need be. So what that looks like, right, is this. Right? Here's my new edge object. This is U, this is V, right? It's this, right? So I'm going to do insert edge. I'm passing in this object and this object, right? So I'm not sending in CHI, I'm sending in the vertex and that vertex. I'm sending them into insert edge, right? So in the outgoing, right, it uses CHI and then this vertex, Miami, and then puts this edge into it, right? So here's our outgoing edge, CHI to Miami, and then that edge. And then it does the same thing for incoming. Incoming, it uses Miami. And then in the map is CHI. And it, too, keeps track of this object. Now, this is kind of messy. So we can kind of think of it like this. Right, where I have the outgoing edge, which is this CHI vertex. And this is the Miami vertex. So I'm writing this, and it looks like I'm putting strings in here, but they are not strings. They're really those vertex objects. And then this is going to maintain that edge object, which has whatever weight was sent along with it. All right, this is the adjacency map, or the way it's done. Now we're going to have ways of going through this. So sort of the starting way of it is we can go through all the vertices, and then we can look at each map on the edge, right? So I'm going to go through all the vertices, right? And I can find them by going through this outgoing map, because all vertices are going to be here in this map. And then I can go to, let's say, Chicago here, right? That would be the first vertex. And then I can go into that vertex and get the edge map out, right? So I can pull out this map here, and then go through that, right? Go through that map. In this case, there's only one in there. And then, I don't know, do something with that edge, right? Because there's going to be a from and a to based on that edge that we can do that. Now, where are the pieces to do that? Well, we can insert edges. Here, it's called incident edges. This will go through all the edges of a single vertex, right? So if I'm given passing a vertex, and I set it to be true, which means it's going outgoing. If I set it to be false, so I'm going to make sure that vertex in the graph. Then I'm going to make my list either outgoing or incoming, depending on how this is set to be true or false. So then I'm going to go through for each edge in here. So this incident edges here handles this part. That way, make it look more like we're doing that, right? So I'm going to go through here, and this code yields each edge, right? So it's iterable, and then we'll go through. Now, there's also all the vertices, right? So this vertices function goes to the outgoing, right, which is a map, and returns an iteration of all the keys in that map, right? So this vertices goes through all of the outgoing keys, right? So in our graph, right, here's outgoing, it would go through this one and then this one, right? So, Ravine Vertices, right, this is an object. It's going to go through here. It's going to pull out the edges, and then we need to access edge pieces somehow. To access edge pieces, we can get the endpoints, which returns a to and a from. Have the to, we can get the from. If we have the from, we can get the to. That's the opposite one here. Or we can get the element that's associated with it. So let's call endpoints and make that. So let's say origin destination equals edge dot endpoints. Right? So I can call this endpoints method. So this endpoint method, given an edge, it'll return a pair of endpoints, and then there's the origin, there's the destination. So this is one way of going through the entire graph. Additionally, you can, where is it? I lost it. You can go through all the edges, right? So we're going to go through and basically take all the values from, let's see, yeah, so we're going to pull all the values out of outgoing, right? So what edges would do is it's going to pull all the values out. So this is this row here, right? So it'll pull this map out, and this map out, and the next map out, and the next map out. So it'll pull out all the maps from here, right, which contain vertices and edges. And then it's going to go through the values of the values, right? So it's going to go into the secondary map, this map from edges is going to pull out all of these values that are in here, which are the edges themselves. I'm going to put them into a set. Sets basically remove duplicates. So we have all the duplicates removed, and then this will give us a list of unique edges that are going out here. So we can pull all the edges out of the list too. There are some other terms, some other things. Here's that validate, which works the same as positional lists. We're going to check to see if this vertex is of the right type, right? It belongs to the same class. Make sure it's a vertex, and make sure it's somewhere in the graph. Otherwise, we're going to throw an error there. So this is going to sort of validate it, make sure it's good, make sure it's in the graph, and make sure it's make sure it's a vertex, and then make sure it's in the graph. Determine if it's directed. We can go through and count the number of vertices in the graph. This makes sure that there's something in outgoing, right? So to look at sort of here, right, there are 2 entries in this map, right, which correspond to there. So there's 2 vertices in the graph. Each of these is going to have its own vertex. We did that one. This counts the number of edges in the whole entire graph by goes through everything and outcoming, and then finding the length. This is a map here, right? Because outgoing is a map. There's the vertex. So it's going through every vertex, right? So that's the same as this. Going through every single vertex and summing up the lengths of the maps, right? So this is saying go through each of these maps. Go through each of these maps and count how many entries there are in here. So it'd be 1 plus 0. In this case, it'd just be 1 edge for outcomes. That's how it calculates the edge count. We talked about edges. If we send in a vertex and send in 2 vertices, right? We can make sure that this is a good vertex, make sure that's a good vertex, and then we can look it up, get that value, which may be none, and then send that back, get edge. The degree of a vertex is the number of edges going out of it. I suppose I should put that in my definition somewhere. So for instance, there's a graph that has multiple, this one. The degree So the degree of a vertex is the number of edges going out. Well, I guess that would be better written. So for instance, I count 2 edges going out of here, so it'd have a degree of 2. This has 1 going out, so this has a degree of 1. This has 3 going out, that has a degree of 3. Okay, so occasionally, for some things, we need to know the degree of a vertex. And I think we've gone through all of these. Now, kind of a messy thing to get to use and to work. So the book has provided examples. And in that comes this method called graph from edge list, which we can use. Well, it's sort of a helper function, but basically what this method or function does is, if I just put together a whole bunch of edges in a list, so I have a list here of pairs, a list of lists or a list of pairs, right, which may be weighted or unweighted. Where's a weighted graph? Here's a weighted graph, right? So here they're weighted, right? They're sets of 3 as opposed to sets of 2. Right? Then this will create a graph from the edge list. Each of these is a function in it. So I'm going to let's actually build a graph. Let's use one of my examples, I guess. Let's see. So when we create a graph, right, we can either make geograph directed or undirected. Oh yeah, I talked about this. So let's make a graph up real quick. And let's call them A, B, C, D, E, and F. Let's throw in some edges. And let's just do that. So in order to take this graph and put it into the book, right, we're going to need to do some things. Okay, the first thing we're going to need to do is we're going to need to make an edge list. I'm going to call it E, capital E, right, for that. And we have, right, from A to C, from A, oops, A to F. These are strings, by the way. And we have from A to E. I'm kind of using each edge as I'm going through in terms of columns. Nothing comes out from E, nothing comes out from F. I have something from C to D. And I have something from B to D also. Let's end my list and put it in there. So there's my edge list. Here's my edge list, right? Oh, I have from B to C. I missed one. I think that's everything. Did I get C to D, B to C? Okay. Oh, I can count. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So it looks like I've got that correct in here. And then I can call this function, right? Graph from edge list. So now this is in a function already. This I'm going to put at the top level. So I'm going to stick in this edge list. And let's just make it look a little bit neater. Interesting. They have a comma at the end there. Comma at the end. I guess you can leave a comma at the end. Have a comma at the end. But I can put this on a separate line yet, so it sort of matches. Okay. So I have my edge list. And then I'm going to say my graph is equal to oops. I'm trying to use Windows here. Okay. So let me not use Windows. All right, so I'm going to call graph from edge list, and this returns a graph. Right, so now my graph is going to be equal to that. And this is called graph examples. And, oh yeah. Here's a local bin Python 3. That looks right. Nothing bad happened. Wow. That's a wonderful thing when nothing bad happens. How can we figure out if it's right? Well, let's use some of those methods we talked about. How about we do an edge count, right? Make sure that there are 6 edges in there. So I need to go into my graph and call edge. It was called edge underscore count, I believe. Edge underscore count, yes. Okay. Yeah, get the right number of parentheses in there. There's 6 edges. Oh, looks good so far. Is there a vertex count? Yes, there's a vertex count. Right. It's vertices, not vertexes. Some people get very upset about that. Not me. I don't care. 6 vertices? Is that correct? Let's go look at our graph. See if it is. Yes. 1, 2, 3, 4, 5, 6. Okay. Now let's traverse this graph. So for the edges first, and look at that. For E in my graph edges, right? This will go through all the edges as we saw before. Let's just print see what happens. That format. Okay, got the right number of closes. Let's also skip a line. All right, well, we get these edges. Right? But I said the edges aren't stored in there. What's happening? Well, let's go back and look at what happens when we try to print an edge. Right? Well, in the edge, there is this method called str. If I try to print something, right, and it's a object, it will call the built-in str function by default. So that's how we're getting the values coming out. I can't actually use these values, but I can look at them and see. And the same thing, I believe, is also on the vertices, right? It's returning the element, right? So this str function is returning the element. So, oh, yeah. There's our edges. Look at the vertex. V. Right, so here's the vertices. Right, notice that they're not in any particular order, right? Because they're not. So I have my edges. I have my vertices. Suppose I wish to go through and well, let's go do the last piece of code I had in the previous slideshow and kind of do it in this way. These would be vertices with their edges, outgoing edges. Right, so I got to go through all the vertices. Right, go there. Right, and then I go, oh, edges, I'm sorry, edges is for the graph. Incident edges is for a node, right? So the graph has edges, but for a node, it's incident edges. First, let me just print. Right, so this is sort of the way of going through in a different order. Right, so just going through the edges or the vertices. Now we're going through edges based on vertices. Well, let's put in a code here. This is a method, not a variable. Let's see what we got. How many mistakes I have. Let's see what I do wrong. It's not called incident edges. Called incident underscore edges. Oh, I need to put in the graph because it's a member of the graph, not the vertex. I'm sorry. So it's the graph and then parentheses vertex. Okay. Graph examples. the way to put it together. Right, so now here's vertex A, right, and there are the edges. Right, there's vertex C, and there are the edges. Oh, it has both the incoming and the outgoing associated with it. There's vertex X, F, there's D, there's B, right? There's E. So now these are all the edges that are going through it. The true, I guess we do need the true here. Yeah. Incident edges. So if I pass true, it only does the outgoing edges. Right, that's that's what I thought it would be outgoing edges, but it's got incoming edges also. I have to look at that a little bit. Anyway, if I don't want to print the edges, I just want to print their values. These are going to be vertices. So I can line that up. Let's indent it a little bit and print the origin. Right, so I have my edge. I'm going to get the endpoint. Got the right number of parentheses. Okay. I have a misconception somewhere. I'm not sure what's going on here. I'll fix that and get back to you on that. Now, one other piece that we have that's important to use with this is this routine here, that how we build this edge list. This is creating a directed graph, and it's creating this set of edges. So it's going to go through each edge in that edge list, take the first element and the second element and add it into its list of vertices. And then it's going to create this extra map called verts. This map called verts kind of keeps maps from the label index to the vertex index. What happens is, right, we have this picture here. In order to find an edge, right, to look up something, we would need to know where this is. Well, this extra verts map maps the strings, right, the things that we're using for the labels, to the object itself, right? So verts of CHI is this object. So I can use that later on as sort of a lookup between the names that we're calling the vertices and where those objects are, right? So that's what this verts adjacency map is doing, right? So it's going through here, insert vertex, returns, right? So G is my graph here. Insert vertex returns the object. So I have a map here from this V, which is pulling it out of the edge list, which is the name, right? So it's going through all the names and storing in the name map, it's storing where that variable is. So when I go to insert the edges, right, I can say source is E1, destination is E2. So for each of these edges, right, it would say, like for instance, Boston, San Francisco, right? So this SRC would be Boston. I can't insert edge unless I have the object. So this verts gives me the object of the source. This verts gives me the object of the destination. So now I can insert edges using, right, because the insert edge routine needs to have, right, not the labels, but where those objects are stored in insert edge. And so that's sort of a complication there with that. Yeah, we talked about the vertices, talked about edges. I just mentioned, yeah, inserting edges. I just mentioned that too. Okay, so this is all rather complicated. So the first thing we're going to do with this is read it and store it and print it. So the lab that goes here. Oh wait, you know what? Let me pause the recording and start it again so I can make it separate.